couple of years, and I was at IBM until I left in 1992. Then I went to university at that point in time.
Test 1, 2, 1, 2.
If you wouldn't mind just using that, this is how you shut it off. Just hold the button, and it will go off. Okay. And just put it back in there. So I'll turn it on for you. You're ready to go.
Thank you.
Thanks so much.
More minutes.
Whatever.
So it's my pleasure to introduce Professor Jerry Woodall. Professor Woodall joined our department in 2012, in July 2012. And as a distinguished professor, he's the inventor of the red LEDs, which is used every day for sure. And actually, he started his career in IBM and then moved to academia. He received in 2001 the National Medal of Technology from George W. Bush, the second Bush. And actually, about more than $2 billion in sales are attributed to his ideas and his developments in technological developments. So it's my great pleasure to introduce Professor Jerry Woodall, who will be giving a talk on global scale solar power derived electricity and energy storage.
Thank you, Phil. Oh, hi, folks. You're all here because you have to be here, right? Okay. Hopefully you'll enjoy it, though, nonetheless. So I had a fairly interesting career. I was able to make really bright red LEDs before nobody cared about it. So my management said, "What's wrong with Edison? You know, you never want to do something really big too early, because by the time it makes a difference, people have forgotten that you did it." So, but I can still hold something in my hand. These PDAs. I actually have two devices that I invented while I was at IBM. One is the amplifier, the HBT, and the other is the preamp, which is called a pseudomorphic HIMP. So at least I showed this to my kids. They could care less that I did anything for it. All they want to make sure is they can talk it and use it all the time. So let's get started. Let's see, I guess I can stand over here because you can all hear me. So Professor Katehi has the theme for this year's 290 EEC 290 series about the fourth industrial revolution. And so part of that, I'm going to talk about the energy problem. And there is an energy problem. So I use the word global scale solar power because the solar energy is 93 million miles away. We don't have solar energy on the planet unless we explode a hydrogen bomb. Then we have it for a few milliseconds or so. But the sun is a long way away. And so all we get is power. And it's intermittent, so I'm going to cover that issue in my talk today. So it's derived electricity, and I'm going to talk about some of the energy storage work that's going on in my group. And I point out parenthetically the information infrastructure, AI and IoTs, they're going to need lots of electricity. So there are three global scale energy issues that need solving before Earth can migrate from fossil fuel to alternative energy on a global scale. So first, the energy in the sun is captured as an intermittent solar and wind power. And currently, this power is mostly transduced into and used directly as electrical power. At night, where I live, there's no sun, so I can sleep peacefully. And every now and then it gets calm, so there is no wind turbines moving either. So that's a problem. The next problem is that people are thinking about moving to a hydrogen economy. But the hydrogen that's manufactured now is not viable fuel for source of energy. It's viable for processing semiconductors, but it's not a viable fuel. And the reason is 95% of the world's hydrogen is made by taking methane and putting it in steam with some nickel, and you get hydrogen plus a carbon footprint. The same is true for the other 5% is made by electrolysis. So basically, all the hydrogen is made by something that has a higher energy value. So who in their right mind, since hydrogen made that way has a carbon footprint, why bother downgrading methane from its high energy value into hydrogen? And if I have a battery, why do I want to make hydrogen from that? We used to call this brain damage thinking in the old days. So, those of you who are enamored with Teslas and Roadsters and like that, I got news for you. The worldwide lithium reserves right now, they're vastly insufficient to enable current global scale current markets that we have, EVs and battery technology to store solar power. I'm not talking about niche. The whole point, the reason I'm staying here, I'm thinking about what we want to have globally. I mean, after all, you can take the oils in your fry pan and run your car on it, but that's not a global technology near as I can tell. And as we learned from Linda last week, humans need and androids use about the same amount of energy, which is roughly 2.5 to 3 kilowatt hours per day to live and function, or function. This number is a little bit higher than some of the numbers I've found in the literature, but we'll use it for the time being. But what she didn't tell you about was that the U.S. humans use about 100x times their needed functional energy. And what is that number? In 2013, 316 million U.S. residents used a total energy of 25.4 times 10 to the 12th kilowatt hours per year. And you do the division, you find out that each person uses 220 kilowatt hours per day. We're hogs, guys. We are real big hogs about this. But there is good news behind all this. For the last few years, even though the U.S. consumes 1/4 of the world's energy consumption and has only 4.5% of the population, the good news is we've leveled off in how hoggish we have become. So maybe there's hope. Okay, the rest of the talk is divided into 2 sections. The first part will be about the work on aluminum, using aluminum as an energy storage material, and then reacting it with water to make hydrogen as a fuel on demand. So I use this title because the government agency likes the word earth abundant. That's a hot word in the government, earth abundant, and light. It's recyclable, all that kind of stuff. So let's talk about it. Why is there not a global scale energy economy? Well, I've already talked about one of them. Let's talk about some of the others. There's a low volumetric energy density. I will show you that in a minute. To low temperature liquid storage, which raises the density, is expensive. It costs a lot of money to do that. Hydrogen gas transport is dangerous and expensive. Furthermore, if you talk to a futurist who cares about energy of the future, you will find that there are 3 features that they all agree on that you're going to have for a long-term global energy economy. One is it has to be abundant and economically recyclable without loss. There goes coal, there goes oil up the stack. It's got to be safe storage and safe transport. So the solution is to use a safe, cheap, abundant, high energy density material for storage, transport, and recycling that can react with water to make hydrogen on demand. Why water? The planet is loaded with water. There's plenty of it. Yes, it's salt water, but it doesn't matter that it's salt. We don't have to use fresh water to make the technology I'm going to describe work. And is there a solution? Yes. So I'm going to hawk aluminum today, and I'm going to show you why it's great. It has a gravimetric density of 8.8 kilowatt hours per kilogram and a volumetric energy density of 23 kilowatt hours per liter. So it's got a lot of energy. So here is the data you will take or look at. I want to point out several things. This thing's got a real cool pointer. Look at that, isn't that nice? So aluminum has the highest volumetric energy density of anything on the chart. It's better than ethanol, methanol, or coal. And the only thing beats it, of course, is nuclear power. Notice those people who love lithium-ion battery cars. On this chart, it's 0. So all you're buying is a big thing that weighs a lot of there. You put in a sexy car and away you go. The other thing I want to point out to you on this chart is here's our friend hydrogen. It's got a great gravimetric density. If I could hold a chunk of it in my hand, we'd be done. Maybe we'd be up here somewhere. But alas, that's not the thing. So even if I take hydrogen up to 10,000 psi, which is the number they're going to use, these 2 numbers for the hydrogen highway, its volumetric density is insignificant. Liquid hydrogen is not much better because it's a low-density material. So let's just focus in on the energy density of the aluminum hydrogen system and heat. So hydrogen from splitting water, we get 1 kilowatt of hydrogen is worth 142 megajoules, or 39 plus kilowatt hours of combustible energy. It's a little bit less if you're going to use that hydrogen as a lower heat value for fuel cells. So 1 kilogram of aluminum makes 111 grams of hydrogen from 2 kilograms of water. That gives us a total of 4.4 kilowatt hours from hydrogen. Okay, so if I have 10 kilograms or 1 gallon of aluminum, gives me 44 kilowatt hours as hydrogen. Diesel's 37. Look at liquid. Hydrogen is only 10 kilowatt hours per gallon. The heat from splitting water is 4.4 kilowatt hours. And so systems that we'll design to use this, we're going to run at higher temperature where the heat value has some value at a Carnot efficiency that's worthwhile. So the total energy for aluminum, 1 kilogram, 8.8 kilowatt hours. Coal is 6.7 kilowatt hours. The energy to electrolyze aluminum is 1 kilogram of aluminum is about 12.9. Those are current values that we use in the industry. The total energy efficiency round trip, using it up and recreating it again, is about 68% for all the energy and 34% for hydrogen, which is about the same as for current industrial electrolysis to make hydrogen. Now, remember I'm talking about global energy here and sustainability. So the aluminum reserve is about 10 to the 13 kilograms, or if I convert to hydrogen, 1.2 times 10 to the 12 kilograms of hydrogen made by splitting water. That's equivalent to 5 times 10 to the 16th watt hours of hydrogen energy, or 170 quad BTU. Just for comparison, the total annual energy consumption for the United States is about 100 quad BTU. The current worldwide production of aluminum is about 52 billion kilograms from bauxite. There are 400 billion kilograms of aluminum scrap that's free lying on the planet's surface. So just go pick it up and you can use it. All right? The amount of heat, so if you look at that amount that's sitting around as scrap, that's enough to give you 12% of the total US energy supply consumption. Okay, so it's global. Oh, one more thing. Just to convince you, we have an industry already. We have a global aluminum industry out there. So we take bauxite, we mine it and extract the aluminum out of it. The alumina that comes out of bauxite is chemically purified to about 4/9 purity. That's the model. It's then sized to a powder with a mean particle size of 120 microns. If Alcoa does it in Australia, it's shipped to one of their 9 smelters around the world where the electricity is about 2 or 3 cents a kilowatt hour. Batches of aluminum with, the model is that batches of aluminum with customer specified impurities are made by electrolysis of the high purity alumina. These are called smelters. And so once I've made, so it turns out that Budweiser likes magnesium in their aluminum. But once I have the magnesium in there, trying to purify that aluminum is more expensive than digging more bauxite out of the ground, at least right now. So that's the model. So we have a global scale aluminum economy. If we can make aluminum split water, we could have a global scale hydrogen economy. But as you all know, you probably have aluminum pots and pans around your house, so when you add water to it, nothing happens. So I have all this aluminum, but there's this 10 nanometer film of aluminum oxide on it that doesn't allow it to react. Turns out the reason for it is the density of aluminum oxide is the same as aluminum, so it doesn't form any cracks. It's very tenacious, and that's the only reason we have aluminum pans. If we made lithium pans, you would have explosions every time you use it. Boom. All right? But what if there was an easy, economical, viable way to remove this oxide? And there it is. So what we do, or what I did back in 1968 or so, is I took aluminum, dissolved it in liquid gallium. So here is our liquid gallium. Okay, so we dissolve these little aluminum in there, that's aluminum. And then we add water to it. This is the chemistry for it. We get 3 hydrogen bubbling out, and we get aluminum trihydroxide and heat. Boy, that is simple chemistry. And it works every time. There's nothing you have to do other than just dissolve the aluminum in gallium. There are other ways that we do it, but this is one of the ways it's easy to do. The reason it works so well is even though gallium is expensive, it's inert. So you can use it over and over again. It doesn't get depleted. So by the time you run lots of aluminum through the process, the yields are really good, and so the cost of gallium is just amortized over the amount of aluminum you process through it, okay? So here's a picture of a little crystallization dish that has aluminum with 1 kilogram of gallium with 25 grams of aluminum, putting out 34 liters of hydrogen in a hood, of course. So that's what it looks like. It's very vigorous. So 3 days later, we have the aluminum trihydroxide after we dry the water off, or most of it. The gallium is still down the bottom of that. And that's what it looks like. The aluminum hydroxide, trihydroxide, is nothing more than alumina with 3 waters attached to it. So it's pure, it's white, and it's high purity. So you can sell it if you want to do that, or we use it in the applications I have in mind. So what happens if you mix aluminum with gallium and melt the mixture and then freeze it? Will it split water? You bet. So here's some chunks of, we take aluminum, in this case only 28 weight percent, 72% gallium arbitrarily, heat it up, melt it down, bring it back to room temperature, and you put it in water, works just fine. Salt water works just fine. So here's some reaction rates from some 50-50 chunks. So we plot the moles of hydrogen against half a gram of aluminum. We don't get 100% yield with this particular reaction, but look at the interesting thing is, if we heat it up to only 60 degrees C, the reaction is very rapid. So, within a matter of, 15 seconds or so, we've almost reacted to where it levels off. Of course, there's some more work on this particular process to get the yields a little bit higher, but they're about 85% right now, which is not too bad. So how does this alloy work? This is really interesting science. So the solid mixture of aluminum and gallium is really not a solid. It contains lots of little regions of grains, aluminum grains, and these grains are surrounded by gallium. That's really critical. So the grains then can dissolve aluminum at around room temperature, which is about 2%. We can go to a higher temperature, more solubility. The aluminum saturated liquid gallium at the sample surface interface reacts with the water to make hydrogen and aluminum trihydroxide. The aluminum pleated gallium now dissolves more aluminum until all the grains are used up, or at least 85% of them. So we have nice little chunks that we can use as a source to put them in a reactor to use it. Here's a cartoon that shows how it works. Here's our aluminum grains. All right. The black region is the liquid gallium surrounding them. This is the little dots here are aluminum dissolved in the gallium solution. And you see, I show this picture just after the surface aluminum dissolved into gallium reacts with the water, making hydrogen aluminum trihydroxide, and we go on from there. And then finally, we keep using this until all the grains are dissolved. This is the process continuous. So we continuously remove the aluminum from the liquid gallium to form hydrogen aluminum trihydroxide, and then it just keeps going until all of it's converted to aluminum trihydroxide, which is not lost. We just recycle it, and that's basically the process. Well, what about the water? Well, if you are forced to use a local water supply, look what happens. So if I look at the chemistry, the water I get, which I use, say, 6-hydrogen for this particular reaction, I now have it in the form of, if I take the hydrogen and react it with oxygen, I get the water back, or either combustion or by fuel cells. Or I take the aluminum trihydroxide, we heat it up, and we get aluminum oxide plus the water. So we get all the water back. And of course, I wrote the reaction in terms of what would happen at the smelter. So you get all the water back. So the nice thing about this thing has a very interesting scale of applications. We can talk about PDAs and stuff like that, where 1 to 100 milliwatts and maybe 10 watt-hours of storage, laptops, PDAs, etc. Then we can talk about vehicles like utility vehicles, cars, boats, fuel enrichment, hybrids, gasoline with hydrocarbons added. That works very well with trucks, raises the gas mileage by a lot by adding hydrogen to the gasoline. Then we can talk about ships, trains, and subs. So there's a whole bunch of scales at which you could use this thing. One of the things that we're working on is to dissolve the aluminum into liquid gallium at 300 degrees C, or 350, have it under pressure where we can use water below the triple point and make the hydrogen at the pressure that we need. Then we'll feed the hydrogen into a fuel cell, store the heat in a phase change material. So that's one of the things we're doing. Here's a schematic of what we have in mind. We have a generator that's going to generate the heat. The heat goes into a phase change material in your backyard. Then you use that heat to do space heating and water cooling and heating. Use some of the hydrogen to run a fuel cell to keep electricity in your house, have a source of water. So all this stuff can be done in your backyard. The neat thing about this is that we can generate this hydrogen at the pressure that goes into a fuel cell vehicle. As you all must know by now, the hydrogen highway is stagnant because there are not many stations around that will deliver 10,000 PS hydrogen into the tanks that have already been invented. But they're there, and they're good tanks. So this is a way of getting around that problem, so you don't have to worry about pumping it, increasing the pressure. You can just make it at the pressure you need. So then we save the aluminum oxide. We put it back, take it back to the smelter, and it goes back and around and around. So we have a complete closed loop process which doesn't disappear. The CHP stands for combined heat and power. You could have these things in a kiosk along Route 80 or in your backyard or in a community. I won't spend any time on that. I'll just keep going. And finally, for those areas of the world where water is really tough in power, instead of bringing in lines and putting roads to villages, we drop in our aluminum alloy and reactor, say a fuel cell, take it in. They can use any kind of water, brackish water, any kind of water, and make hydrogen. We can use a fuel cell to make electricity, and then store the spent material, and for later pickup. And if you don't store it, it's not a big loss. So if you don't recycle it, you can do this for $1 a gallon of water and 34 cents per kilowatt hour for electricity in a remote village. So it's a very interesting possibility. We haven't tried to explore that anywhere, but we'll get around to that at some point in time. Finally, here's the cycle. So we take our aluminum water, we react to get hydrogen, aluminum trihydroxide. The gallium goes back because it is not lost. So now we take the hydrogen and we either use it for a fuel cell or combustion. We get electricity, we get water. That water can be potable, or we can use it to go back in the process if we need to store it. Likewise, the aluminum trihydroxide, you heat that up, you get water back. You either reuse it or you turn it into potable water. So these are the numbers that we get: 3.73 kilowatt hours of energy, lower heat value for a fuel cell, 2.89 kilograms of aluminum to recycle per kilogram of aluminum, and 4.42 kilowatt hours of heat energy. So the bottom line of topic 1 here is aluminum. It's a global scale, earth abundant material, high energy density. There's plenty of it. It's the third most abundant element on the planet. And once you buy it, it's yours. It doesn't go up the smokestack. So think of aluminum as coal without carbon, and it's recyclable. How are we doing? All right. Now I want to talk about energy storage by another form. So that we have to face the challenge of intermittent solar and wind power sources, okay? And so what people want is to be able to have electricity 24/7. And of course we can do that nicely with fossil fuels because it keeps running and running and running day and night. But the sun sets and the wind becomes becalmed. So the things that rely on solar power to make wind and solar power, the thing I will show you is that all you get is 1/3. I don't care how many solar cells you have. If you don't have energy storage, you're never going to get more than 1/3 of what the planet needs. Okay, so I started thinking about this solar power thing. So I called up the administration, the current one, and they said, no problem, we got plenty of coal. Besides, we can take that coal and make electricity, feed it in here so that when the wind dies, we can take these fans and drive the windmills. Now, for those of you who submit proposals to government agencies, you should be laughing, or you should be crying, actually, because this is the kind of mentality you get back when you get your proposal reviewed. It's sort of like this. Anyway, I always like this thing. It's kind of a fun thing. Okay, so now let's take a look at this. The sun is the source of life and all the energy we have, actually, except maybe nuclear. And of course, the hydrothermal energy, which is coming from the center of the planet. So let's take a look at this. So we have solar power. So it's converted to stored energy. This is for humans now. And we can convert some more of that to other forms of stored energy. And finally, we can convert this to a biopower. Okay? Now, what are we talking about, folks? 7 billion people on the planet, they need 4 times 10 to the 15th watt-hours per year of food to sustain life. That's the minimum. Okay? Well, we got 5 times 10 to the 13th meters of arable land, which gets 10 to the 20th watt-hours per year of solar insolation. Sounds whoopee good. But what you find out that the conversion of solar into kilowatts of energy into stored food is about 10 to the minus 4 or less. This is a very liberal number. So right now, we should be able to do all this stuff. But if we get too many more people on the planet, we might have a problem with doing that. So the point of this particular slide is that nature, or evolution, whichever you prefer, perfected the conversion of intermittent solar power into stored energy, then back into 24/7 power, okay? Whoops, did I miss one? Nope. Okay, I'm sorry, I put this in the wrong order. So let me show this anyway. So here's what we do. So we consume 3 times 10 to the 16th watt-hours per year, or in 2015, or quad BTUs, 97. Those are the same numbers, just energy conversion differences. We waste more than we use of it, just 60% almost, and this is what we get back out. These are the waste numbers going out of it. So this is where it all comes from. Notice that alternative energy in 2015 hasn't changed very much, doesn't account for very much now. So the biggies are the things that we're using right now. Okay, so let's take a look at that. So we found a way to use stored energy derived from the sun that may destroy humans. The problem is, so all this energy that we're using that's been stored occurred over a long period of time. So the rate of formation was infinitely slow, and now we're using it up very fast. So I don't know, I haven't seen any dinosaur farms lately or anything like that, so I don't know. They talk about biogas and stuff, but then it turns out there's not enough land to do all that. I won't even go into that argument, but it's true. So there's just so much land that we can do or get biofuels that way. Of course, the point is all this is carbon-based, and so carbon-based is not good, it's debatable. Okay, so 95% of our energy is coming from all these sources: gas, coal, oil, nuclear. So over here we got our we got our power towers where we take mirrors, heliostats, make it hot, try to convert to energy, power actually. And we have solar rooftops, and we have the wind. So most of the solar power conversion is into electricity. There's a couple things that we get that are stored. One is the geothermal energy, but there's not enough of that to satisfy everything on the Earth. And there's not enough dams that we can possibly do to meet the global needs for energy. No economically viable way to convert power to stored energy on a global scale. So if you students want something interesting to do, that's it. I don't know what the jobs are paying, but it's certainly needed. we're kicking the solar power storage down the road. So, as you know, California is great on putting solar panels on the roof. You either own them or you rent them or rent them from a dealer. So that's pretty cool, but look what happens. So PG&E is forced by law to buy electricity from folks who have installed PVs on their roof, and then while you're away at work, your meter is running in reverse. So you come home at night, it goes the other way, and if you're lucky, you don't have an electric bill. Without this forced subsidy, which has been halted in Nevada, the solar cell market, the PV market, will become a niche market. But here's the thing. I love this so-called duck curve. The blue curve was the demand on October the 22nd, 2016. So you can see it's up about megawatts, 20,000 megawatts. And it goes up goes back down. What PG&E gets money for is the red curve. Okay, notice that it dips down. And this dip is due to all those wonderful people who have put solar cells on their roofs, trying to be nice. But the utilities folks are taking a bath during the day because they don't get any money for that. So during the day, as you can see, not during the night, but during the day, they're selling this power back to these guys so the total power needs are being met. Now, if everybody in California decided to put solar cells on their roof, then we wouldn't have any utilities and you wouldn't have any power at night. How about that? Whee! All right. Okay, with their global solar cell grid technology. Okay, so here's the problem. Oh, you see all these wonderful ads about First Solar making modules now for 50 cents a peak watt. But what you don't know is when you put all these together into a system, which electrical engineers do, that turns out to cost about $5 a peak watt, whereas you can still, if you want to buy a gigawatt plant, it's going to cost you $1.5 giga dollars. And so if I were going to invest money, I would invest it in utilities making fossil fuels, not solar. The inventory only works 33% of the time. Without storage, fossil fuel has to be used to give us a 24/7 electric power or nuclear. So that, folks, is the issue. That we're doing okay. Second problem can be solved with intermittent solar or wind capture conversion to heat, storage, and its delivery as thermal power on a 24/7 basis. We are trying to do that. A quick word about solar cell. Here's a picture that you can't read. Well, I want to point out to you, when things got started back here, I happen to be the lucky recipient of having the world's most efficient solar cell. Was twice everything out there. It's gone all the way up to about 29% now. What I want you to see is there's some cells up here that are very efficient. There's some cells down here that are not very good, and there's a bunch of stuff in here. This stuff is not going to make it, and I'm going to tell you why. These things are just not quite efficient enough, and so even the ones that are here, which have a chance to be a rooftop cell, these are laboratory numbers, and by the time you turn these laboratory numbers into rooftop cells, you're down to about 14 or 15%. Efficiencies really matter in the total cost of the system because you got the land issues, you got the support costs, you got all kinds of things you got to worry about. So those concentrator cells, I'm not going to go into a big lecture of how they work, but if you take lots of different cells with different band gap energies and stack them on top of each other, you can get to an efficiency nowadays at 46% with 500 suns, which means I'm coming in with 50 watts per square centimeter, which is pretty hot, a pretty focused heat. Okay, but to be able to get to these 46%, they have to use only a 1% duty cycle. Well, the sun's there CW, so that doesn't make much sense. By the time you use it in a real system, you have to cool the material. So the bottom cell, which is a low band gap cell, still works. And by the time you add up the energy and the cost for doing that, the efficiency, system efficiency drops to about 25%. So that's all I'm going to say about that. So let's talk about the summary of global solar PV for a moment. There's a conundrum. So the total annual worldwide energy consumption is 1.3 times 10 to the 17th watt hours. That's all. It's a lot of it. Total possible annual energy from sun power, assuming a 15% cell using just 10% of the arable land, we're talking, we do the numbers, it ends up to being 1.6 times 10 to the 18th watt hours. Well, heck, great. Whoopee. Without storage, two-thirds of the global energy load will have to be supplied by fossil or nuclear power. And hence the subtitle of my topic, 1/3 ain't enough to justify global installation of PV. So I don't care how excited you are about sun and solar cells, we are missing a major ingredient. We can't do it with batteries. We gotta pick things that will store energy at a large scale. Otherwise, there's not going to be any reason to change, because you didn't know this. I remember, real quickly, when I was growing up a long time ago, they used to have these charts of when we run out of oil. It was somewhere around 2010, shifted around. Well, we got plenty of oil. What the chart didn't tell you, that's all the oil we had at $20 a barrel. If we spend $100 per barrel, we got another 350 years in the United States for oil. We're not going to run out of oil, folks. So in order for this stuff to work and that people are going to change, it has to become economically viable, unless the government, which I don't think is going to happen anytime soon, decides that we really have to cut back on the use of fossil fuels. It's as simple as that. We're not going to run out. It has to be another argument for moving over to this, okay? Let me finish up real quickly here now. Okay, so a potentially important economically and technologically viable way to store solar power on a global scale. Capture the solar power as heat power and store it as a phase change material. So what the hell is a phase change material? And you guys ever had ice water? I put ice in some of my mixed drinks. You know, bourbon and ginger. Oops, you guys are too young for that. Okay, no, you're graduate students. All right, so here's a phase change material. So we have a student working on that, a program. The idea here is we bring in the power while the sun shines, or we could actually use electricity to heat up. We bring in the sun, concentrate, have a selective absorber. This is a selective absorber is something that will absorb most of the solar energy, but won't re-radiate it as heat. That means it's got an emissivity that varies with wavelength, that we won't go into that today. So now we need a material like ice, except this ice has a melting point of 577 degrees C. So we call it a phase change battery. So if this runs right, we can use the sun while it's shining plus store it, and then we can run a light bulb. Here we show using a thermoelectric generator because we can get those easily. They're not very efficient yet, but that's what we will do in our project. So here's for those of you who know something about material science, here is a phase diagram. So EE guys go, yuck. Okay, so let me tell you how it works. So what we do is we make a liquid right here, and when we take it here, it suddenly freezes into aluminum, and over here, it freezes into silicon. But the point is, the composition stays the same, so you can add energy to melt it and take energy away to freeze it. Okay, and the little lecture for that, it shows the stored energy. Latent heat is much better than sensible heat. That's why we put ice in drinks so they can sit on your countertop and stay cool at a constant temperature. The beautiful part about having this material here is just like at ice, it stays at a constant temperature. So if I have liquid in equilibrium with the solid phase, even though I'm putting in heat or taking it out, the temperature is constant, which is really a good thing to have for phase change materials. This is also being studied by a group led by Chang at MIT. Okay, so let me show you another way of doing this. One is to go to real high temperature. It turns out that silicon is a wonderful material. So we know it's wonderful because somebody gets $350 billion a year selling chips around the world. But it also has a very interesting property that it has a very high latent heat of fusion, and it melts at a very high temperature. So this is something I invented back in 1982 when I was at IBM. The idea is to have silicon in here. During the day, you let the sunlight in, or you could have heaters inside this thing. We use boron nitride, which is a high temperature material. We insulate it. And so while it's running, we melt it down during the day. And so down here we have a photovoltaic cell that's tuned to whatever's coming out of this thing. And we can tune this so it's a fairly narrow band of energy so that the solar cell or the photovoltaic, called a Thermo photovoltaic cell, puts out a very high efficiency, works at a very high efficiency. Well, that was it. But it turns out people are actually working on this. So these folks in Spain are working on this thing. Same idea. They have this material in here as the phase change material. They call it a thermo photovoltaic generator, which is correct. So the idea is I can heat it with electricity. I could have this in at night, and I could use this thing to get it melted down. And I could take concentrated solar light that I just showed and do it that way. So this is actually a worthwhile idea because there's plenty of silicon. Silicon is the second most abundant element on the planet, and aluminum is third. So we are not strapped for what we need to get the job done. Okay. Perfect. I timed this guy just right. Unbelievable. So anyway, without global storage and economically viable electric storage, scale and economically viable technology, global PVs are only going to supply a third of the needed energy demand. Even with global technology, the entire PV system may be too expensive to displace all fossil fuel usage. I mentioned that before. We're willing to pay $100 a barrel. Everybody is. And there's plenty of oil at that price. You may not like how they're making it with fracking and everything, but that's a social issue, and I'm not going to go there. If PV systems are to become global scale storage technologies, like I described, need to be rapidly developed. So it's a good university project. It's good to get in bed with a company if you have good ideas. I recommend it. I don't think the government's going to get excited about it because it depends on the administration where they get their orders from. But certainly GE and all these other companies, if you show them a viable way of getting there and a technology enabling device, they may go for it and start funding you. Okay, all right. So this is a tongue-in-cheek part of my conclusion. So some of you in here have watched the Terminator series. Some have not. You may be too young. But there's a whole bunch of movies by Schwarzenegger, which turns out that the guys who are working on AI and IoT, they lost control. Now, Elon Musk, believe it or not, has gone around giving lectures about that issue. So I think you should be worried about it. And the reason is, when people discovered atomic fission, they say, oh, this might be a bad thing to work on. Well, who stopped them? Nobody did. Nobody's going to stop the Terminator. So think about it as you do your work, especially you young electrical engineers. There's going to be some moral issues, just like there is with cloning and everything else. And so, as I said, this is tongue-in-cheek. But since Elon Musk is going around giving talks about it, it's not that far remote from doing that. So with that, folks, I'm going to end my lecture and take questions. I got a few minutes to do that. Way in the back. I can't hear you. You'll have to tell me what he said. Oh, the aluminum reactor? Oh, I'm going to make it enough for a week in a community. Or I'm going to put it, or I can put them along Route 80 as a kiosk to supply hydrogen to fuel cell vehicles. So we're talking big ones, 1,000 kilowatt hours. That's doable.
How far is that from being commercialized?
Are you asking how far along we've gotten? Okay, so we've been working on this for about 5 years. We're trying to partner with the big boys. Well, actually, what I'm trying to do is I've had some contact with Honda because they have a fuel cell vehicle, and I'm trying to get them interested. There's only 2 of us, so it's not a real company, it's just 2 of us. And we're trying to make technology. So if you were to go into the hamburger business right now, or suppose you want to compete with FedEx, you couldn't do it with one plane. You would have to get enough money to make an impact suddenly. So in 1948, Ronald, whatever his last name is, I can't think of it right now, he only had 1 hamburger stand, but it worked okay then because there weren't any others. Now there's plenty of energy alternatives, so what I have to do is I have to get in bed with somebody who really wants to develop this. All I can do is license the patents I have. Does that answer your question? But I have students working on the science in my lab. Come by and see me if you're interested.
What is the current environmental impact on the exchange materials batteries?
Current environmental impact.
Oh, that's the beautiful part about it. Okay, so if you remember at the beginning of the talk for aluminum, there's plenty of aluminum already being made. That's why I made the issue that now we have an aluminum economy that won't be perturbed. Now, you raise a good question. It turns out the way we are smelting aluminum is that we use carbon electrodes which get consumed. Not a good thing. But other companies have developed titanium boride as a good electrode. It costs a little bit more. Well, if nobody's going to complain about carbon, they're not going to pay extra. But if it turns out there's a new business that requires that you don't make any carbon footprint, we're in business. Because now, if I can take aluminum oxide back to aluminum by smelting it carbon-free, I don't have to worry about carbon when I react the aluminum. So that's not going to be a big deal. And of course, creating aluminum oxide, it'll be small. Turns out there's 150 billion kilograms of aluminum oxide, 150 million metric tons of aluminum oxide made each year. And I can drop it in the ocean, I won't hurt anything. Aluminum oxide's inert. Did that answer your question?
Yeah, but how about because you also mentioned aluminum silicon?
Aluminum silicon.
The aluminum silicon? Oh, that's what we do. It's like ice. We melt it and freeze it. It's an inventory. It's cheap. It's metallurgical grade silicon, which is dirty, and dirty aluminum. All we care about is freezing and heating it and freezing it. That doesn't have an environmental impact because it sits in a container forever. It doesn't get used up. Thanks for your question. Anybody else? Hydrogen, and the same for heat.
When we are converting the aluminum oxide back to aluminum, how much is the energy required?
Okay, so that takes, with current technology, measured, actually being practiced, 12.9 kilowatt hours per kilogram of aluminum. That's why I said if you use both the heat correctly and the hydrogen, you get a round-trip efficiency of 68%. I got to tell you a funny story, because I had a very sophisticated colleague at IBM who said, yeah, but you have to put energy back in. I says, yeah, well, you have to dig the coal out of the ground, so that's for free. This is not for free. We live by thermodynamics in our laboratory.